This is Dr. Karnik with New Age Science Academy. And in today's session, we are going to be looking into how to calculate pH for a strong base and a weak base. In our previous session, we looked into how to calculate pH if you have a strong acid or a weak acid. Let's look at the question we have today. The question is, calculate pH of the following solutions: 0.225 molar KOH and 0.1 molar NH3. The Kb value for NH3 is already given to us. So let's look into the first solution. We have KOH here, and we know that KOH is a strong base. Calculating pH for strong bases is the easiest thing to do, very similar to how you calculate pH for a strong acid. This is because strong bases are going to completely dissociate. So whatever amount of strong base is given to you, you know that each and every molecule of that is going to dissociate. So now let's put down the equation for KOH. 0.225 molar KOH. So you have KOH will dissociate into K plus and OH minus. Once we have the hydroxyl ions, and we know the concentration of the hydroxyl ions, we know that we can calculate the hydronium ion concentrations using the formula hydroxyl ions and hydronium ions. When you multiply the concentration, this is equal to 1 times 10 to the negative 14th. So let's first start with calculating the hydroxyl ion concentration. And this is how we will get the hydronium ion concentration. And once you have the hydronium ion concentration, we know that for calculating pH, we can calculate pH by negative log of the hydronium ion concentration. So in this case, let's start with hydroxyl ion concentration. Here, since we have 0.225 molars concentration of KOH, we know that this is equal to 0.225 molar concentration of hydroxyl ions. Again, because every mole of KOH is going to get dissociated into hydroxyl ions. So now let's put it into the formula. 0.225 molar concentration multiplied by hydronium ion concentration, which we don't know yet, is equal to 1 times 10 to the negative 14. And when you do the calculations, your hydronium ion concentration comes to 0.225. And now all you have to do is substitute this concentration into this formula. So your pH value is going to be equal to negative log of and when you calculate this value, your pH value comes to 13.35. This is going to be the pH of this solution, which is a strong base. 13.35. Now let's look into how to calculate pH for a weak base. The second example given to us is a weak base, NH3, and we can see that this NH3, the Kb value for the NH3 is also given to us. Now, whenever you're working with a weak base, always remember that the weak base is never going to dissociate completely. It is going to partially dissociate, and therefore you will find that to calculate the hydroxyl ion concentration, you will have to look into the concentration at equilibrium. And to calculate the concentration at equilibrium, obviously we are going to need the ice tables. which will tell us what is the value of each and everything that gets dissociated at equilibrium. So let's put down this equation first. And always remember, when you're working with any questions pertaining to acids or bases, always remember the first step has to be putting down the equation. That's going to give you a clear view of what's happening inside the solution. So let's put down the equation. NH3 combines with water, and I'm going to put down, this is aqueous, this is liquid phase. Since this is a weak base, I'm going to be showing reversible arrows. It's not completely dissociating, and you are going to get NH4 plus ions, and you are going to get hydroxyl ions. Again, both are in aqueous phase. Now let me put the ice table. Again, the ice table stands for the initial concentration, the change that is happening till it reaches equilibrium, and the concentration at equilibrium. So the initial concentration given to us is 0.1 molar. So I'm going to put 0.1 here. We don't take into account the water since it is a liquid. In this case, this is going to be 0. This is going to be 0. This is the phase when you just start with the solution. It has not started dissociating. Then let's look into the change. As we know, as it changes towards equilibrium, the concentration of the reactants go down and the concentrations of the products go up. How much does it go down by and how much does it go up by? For that, you will be looking into the balanced chemical equation, and we know that for every mole of NH3, the concentration going down, you are going to be making the same amount of moles of NH4 plus ions and OH minus ions. So in this case, let's say if I say that the value is going down by X, here the value is going to also go up by X and X. So at equilibrium, you're going to have 0.1 minus X, X and X. Now let's look into how to calculate the hydroxyl ion concentrations. For that, we will be using the formula Kb. And remember, here we are looking into the Kb because we are looking into a base. And this value, the dissociation constant at equilibrium for the base is equal to NH4 plus ion concentration at equilibrium multiplied by the hydroxyl ion concentration at equilibrium, and this value at equilibrium as well. So let's substitute these values that we got at equilibrium. So this is going to be X times X divided by 0.1 minus X, which comes to X squared divided by 0.1 minus X. Now let's look into the Kb value given to us. This value is very small, which is again telling us that the dissociation happening is very small, and therefore it reaches equilibrium pretty fast, right? The only way you would have a low dissociation constant here would be if the amount of products were very less, right? So in this case, if the change that is happening is very less, the value of X is going to be very small. And if the value of X is small, we can conveniently disregard this X value, and we can say that when disregard this X value when we are subtracting it from 0.1, because 0.1 minus, let's say it is 0.00005, it's going to be a very small number, right? It's not going to be much of a difference. So we can definitely write this as X squared divided by 0.1. Now, Kb, which is 1.76 times 10 to the negative fifth, is equal to X squared divided by 0.1. You solve for X and your X value comes to 1.33 times 10 to the negative third. Now this is the value of hydroxyl ion concentration at equilibrium. So we are not done yet, because for pH value, we need the hydrogen ion concentration or the hydronium ion concentration, right? So this is the hydroxyl ion concentration at equilibrium. We are going to now use the formula hydronium ion concentration multiplied by hydroxyl ion concentration is equal to 1 times 10 to the negative 14. You substitute the value of OH minus and your hydronium ion concentration comes to 7.52 times 10 to the negative 12. And then when you calculate pH, which is negative log of this value, your pH value comes to 11.124. So in this case, when you are looking into the pH of a weak base, the weak base pH in this case is 11.124. This is how you would go about calculating pH value when you are given a weak base.